All right, let's go ahead and get started. So my name is Bryce. I'm an undergraduate at LSU. I've been working with a research group there, and I, along with my colleagues, develop some software that uses Boost.Asio and Boost.Serialization. I'm going to kind of talk today about how we use these two libraries together to transmit objects in between different machines and send them over networks and do some cool stuff with them. So we work on this thing called HPX, which is, we call it a general purpose runtime system. So that just kind of means it manages aspects of the execution of programs. So it's just a fancy word for a library that's really intrusive in your code. So it uses this asynchronous methodology. We use it for parallelism. So stuff like std async and std futures, but at a sort of much larger scale, running on supercomputers, mostly for scientific applications. So again, we're just going to sort of talk about how we use these two libraries. And so Asio is the networking part of this duo. And we're going to talk about that first, and then we're going to talk about serialization. And that'll probably cover about the first half of the talk. And then we're going to talk about how we use them together and how we build systems with them. So all the code, so this is a talk I've given a few times, and all the codes in this GitHub repository. I was going to clone it to a new repository that just changed the name for this talk, but there weren't actually really any changes in the example code, and I didn't really want to create another repository. So you just go right there, you can get all the code. And there's a couple things in the slides that'll be a little different from all the examples. Specifically, I've taken out all of the error handling so that everything will fit on here. You shouldn't do that in production. I would not advise doing that. And you should sort of assume all of these following. So whenever we have an error code, that's going to be a boost system error code. Whenever you see this namespace PO, that means program options. Because again, that's long. I don't want to have to type that in the slides. And for Asio, we're just going to use this namespace Asio. And then we'll have this type def for this Asio TCP type, which we're going to use a lot. All right, so Boost.Asio is the first thing we're going to talk about. So Boost.Asio is a library for synchronous and asynchronous I/O. So it's usually used for networking, but it's usable for all sorts of I/O events. And in fact, it's just usable in general for managing asynchrony. It's a very general purpose framework. So it uses a proactor-based design. We'll talk about that in the next few slides. And here's some of the things you can do with it. So network sockets is sort of a canonical example. Files, serial ports, direct memory access, inter-process communication, stuff like this. All right, so this is sort of a diagram of what the proactor model looks like. So the short version of what the proactor model means is that it's a model of processing events. And the idea is that anytime an event comes in, that is an asynchronous sort of thing that we're dealing with. So each event is dealt with asynchronously. And what the proactor model means is that instead of something like a reactive model where there's completion handlers that are processed synchronously, in a proactor model, the completion handlers are also asynchronous events. So you have every different message that comes in, every different thing that happens has two asynchronous events associated with it. The thing itself, and then the thing that happens in response to it. And this is kind of cool because you can kind of chain these together, because then you can have a response to the response, and a response to the response to the response. And they're all sort of these asynchronous events in this system. So we've got this sort of asynchronous operation. That's something like an async read or an async write on a socket. That's sort of where we start off things. So the initiator, so that's you, goes and creates this asynchronous operation. And it gets passed off to some processor. Maybe it's some thread somewhere. It's some object that abstracts some thread. It's something that's going to, in the background, take care of starting that operation asynchronously. So it's going to execute the thing. And then it's also going to enqueue this completion event, which represents, hey, when this thing's done, we want to be able to do stuff with it. And then you've got some proactor, something that's going to pull off those completion events, and it's going to go ahead and invoke your completion handler. And so normally, the thing that's going to be handling both your asynchronous events and your sort of completion handlers, that can be the same thing. You can sort of have one sort of process sitting on the side there that's dealing with your sort of reads and writes, and you could have the same process that's also doing your completion events. Sometimes you might want to have two. You might want to have one set of threads that's just dealing with I/O stuff, and then one set of threads that's just processing your completion handlers, because those are sort of different intensity tasks. All right, so Asio works with buffers. That's sort of your most basic data structure here. So there's a couple different types of buffers. So a buffer is just a tuple. It represents an address and a size in Asio. So we've got a bunch of different scatter-gather operations. So scatter reads are just reads that read into multiple buffers. And then we've got gather writes that transmit into multiple buffers. So there's two basic types of buffers. You got your constant buffers, which are usable for writes, and then you've got your mutable buffers that are usable for reads and writes, and they're, of course, convertible to const buffers. So then we've got our streams. So these are I/O objects. Usually this would be your socket, your file. So it's got a continuous stream of bytes that we can read from or that we're writing to. So there's no real message boundaries. There's no concept of different types of messages. It's just a bunch of bytes in a sequence, and you're going to be able to pull them out in a linear fashion. So in Asio, you can have sort of short reads and short writes. So you don't have to read everything that's in the stream, and you don't have to write everything at once. So typically what you'll do is you'll sort of read the first part, like you might read the message size, and then you read the message, because you know how large the message size is going to be. Oops. So there's three different models here. So there's the sync read stream, which is just synchronous reads, read sum. So hey, give me some of the bytes from here. Async read stream, which is, hey, launch this asynchronous read. When it's done, call this completion handler. And the same thing for sync writes and async writes. So the kind of usual example is the basic stream socket, which is for just doing any type of socket programming. So you've got your protocol and your service. And then you've got basic serial port for if you just want to read from a serial port, some embedded device. So now we're going to sort of walk through this echo server example. So I like this because it's very, very short, and it implements a very simple TCP echo server. So here, the I/O service, this thing here, this is our proactor. So that's sort of this thing that's going to be doing our, I need to go back to the last one to get my notes. So that's the thing that's going to be actually sort of processing those completion handlers and those events. And so then if you remember from that sort of picture of the model, we had sort of that demultiplexer. So that's going to be when we call run, which we'll do down there. So then we set up our endpoint. So just setting it up on the local host on port 2000. And then we create this acceptor, this TCP acceptor. And so then here we're in this for loop. We're going to create a socket every time in the for loops. And then we're going to wait for somebody to come in and send us some message. And then we got some buffer here. And again, remember, an Asio buffer doesn't actually allocate memory for you or anything. It's just an address and a size. So here, this is the actual buffer. Now we're going to turn it into an Asio buffer object. But we could use a vector. You could use whatever you wanted here. It could be on the heap. So then we've got this std function f. And this is going to be sort of our the actual meat of the program. So this f represents the sort of sequence of things that are going to happen in the callback. So this f will be passed as a callback every time we do an async read sum. So there's two lambdas inside of here. First one is the outermost lambda is the read sum. So we've got a message coming in. So we've got to read it. And then what we want to do, well, it's an echo server, so we just want to write it back. So inside of this lambda, we're going to start another asynchronous operation in async write. And then once that async write's done, what do we want to do? Well, we want to read again. So we just go and we set up another buffer, and now we're passing in this same f, which is actually the thing that we're inside. So this lambda here is f, and we're passing it to this read sum. So the idea is that you're going to do read, write, or read, or write, or read, or write, and it's just going to keep doing that until somebody Control-C's the program. Oops. Let me see if I can get it back to... And so then down here, we kick off the thing. I go in socket async read sum, and that starts it all up. And then we do the IO service run, which is just saying, hey, IO service, go ahead and process my events. So this is a single-threaded server. You might want to call that IO service run in a different thread and immediately go back into your acceptor loop in a threaded server. Because right here, if somebody comes in and is trying to connect while I'm processing my completion handlers, well, I'm doing other stuff. I can't really process that except right now. All right, so on to the Boost serialization sort of intro-ish part. So Boost serialization is a library for turning C++ objects into sequences of bytes that we can later turn back into that same object in a portable fashion. So serialization is sort of this process of turning it into the bytes, and then deserialization is turning it back into an object from that sequence of bytes. So there's a number of different libraries that do stuff similar to what serialization does. You guys may have heard of protobuf or S11N. I like serialization because I don't think any other C++ serialization library has the same features of Boost.Serialization. So this is the single most important one for the work that I do, which is support for the serialization of derived classes from base class pointers. I think this is really important because other frameworks, you're sort of forced to, if you want to do this, you have to sort of get rid of that information. You lose information in the process if you have to do some weird hackery where you're going to figure out what the actual derived class is. Well, then you're just sort of doing duck typing, and you're not, you can reconstruct it later maybe, but I really like the fact that this is a native thing in Boost serialization. That I don't have to do any special magic to make this work. I can just use my base class pointers out of the box. So it's got data structure versioning, which is very important for compatibility reasons. Built-in support for the STL containers and Boost data structures. This is another big one for me, because I don't want to have to go and write the support for Boost shared pointer, because that's not a fun thing to try to figure out how I'm going to serialize that. Or for any of those Boost data structures. Some other frameworks support the STL containers, but I use Boost a lot in work, so I like the fact that it's got the built-in support for both. So yeah, Boost shared pointer is really one of the tricky ones. And it's got multiple different formats, and you can write your own. So it's got a sort of binary format, text and XML. So for my work, we use a sort of better binary format where we have much smaller messages, sort of a compressed version. And we have an archive where we can actually just run it through gzip to get even smaller messages. And it's got object tracking. So this is sort of important for if you've got, I try to serialize a couple different pointers to the same object. It'll figure it out, and it'll only put it in there once so that you don't have multiple copies of the object. And there's both an intrusive and a non-intrusive interface. So again, for me, this is a really big one, because I work with a lot of scientists who've got code that is older than me that I can't change or add a method to the data structure. So having a way to add support for a particular class without having to go and modify the class is really nice. So there's two different types of archives that you deal with serialization. So first, you've got saving archives. So this is, these are the ways, the syntaxes for it. So you can do sort of the stream style syntax, or there's this overload of the AND operator. So this is saying save a sequence of bytes that represents X to that archive. And you've got loading archive, kind of does what you'd expect. So this is saying, hey, I've got this thing X. I want you to read from that archive a sequence of values that's going to be converted into this X. There are some other type requirements, but they're not really important for our understanding here. So this is sort of the important thing. So there's this serializable model. So it's something serializable if it can be used with these two archive types. So primitives, STL containers, Boost containers are all serializable if you just include the right Boost serialization headers. So it's serializable basically if it's got a member function that looks like this. So this is the intrusive form, something that you've got to add to your class definition. Or if there's a global function that looks like this. So both of these versions, you've got a function. It's going to pass in the archive. It'll work with any type of archive. And then it's going to pass in a version. And then it's your job within that function to define how you're going to serialize it. And it's usually pretty easy because your classes are either composed of data members that are one of these types, or if they've got a data member that's not one of these types, then you have to go and write a serialization function for that type. But so it's, you maybe have to write a couple of these functions, but at the end of the day, you get down to just your sort of primitives. So primitive data types, your STL containers, these basic things we can serialize. So here's an example. We got some coordinate, and we want to be able to send it over the wire. So we write this serialized data member, and it's pretty easy. We just say, hey, serialize X and serialize Y. And here's an example of we're just going to send it out into a string stream. So we're going to use a text archive. So here we've created the archive, and we've got this coordinate 17, 42. And here we've saved it. And note we're keeping this archive in scope here because it's sort of going to be, we want it to go out of scope and to write before we start to do the read. So then here we're going to print out the string stream, and you'd see, well, we'll see what it prints out in a second. And then we've got the input, and so it's sort of same sort of thing. Create your archive, read it in. All right, so when you run this, and note the first thing here, when it's printing this out, this is printing out what the archive looks like, because this text archive is backed by the string stream. And then the second thing we're going to print out here is the reconstructed value. So again, this first line here is what the actual text archive looks like. And then the second one is just the reconstruction. So yeah, it's correct. It gives us 1742. So the first part here is the signature. So the 22 is just sort of an identifier for the version. And then it's got sort of that serialization archive is sort of like a magic byte that some files have on, I think, Windows is the platform, where you sort of got some identifier that says, hey, this file is a particular type. So you got that serialization archive string in there just so that we know, hey, this is an actual archive. This thing isn't just some random data that you gave us. And we've got the archived version. So that's sort of your internal version. That's independent of the serialization of Boost Serialization's versioning. That's you can change the version because maybe you want to go from your two-dimensional coordinate to a three-dimensional coordinate. So you bump the version from 10 to 11. So that you know that if you try to read in one of the old ones with the new code that's 3D code, it'll give you an error saying, hey, that version's too old. The next here is you've got the class ID, which is 0 because we've just got one class, the coordinate, and then the class version. And there's nothing in there where we assigned the class of version, so it's just got a version of 0. And finally, we've got the actual representation of the object. So in the binary archive, it obviously wouldn't look like this, but it would be similar. You'd have sort of all these different parts. So you're going to only have one archive version for the entire archive, but then for sort of each class, you're going to have the class ID and the class version. And for each instance, you'd have the representation of the object. All right, so let's talk about serialization of derived classes through base class pointers. So this requires explicit registration of the derived class with serialization's class registry. We actually have some cool hacks now that allow us to get around that and to automatically register classes at runtime. And that's sort of in the last slide, so we'll maybe talk about that. But in the regular use case, you can just use explicit registration. And this is necessary because we need to be able to, we need to make sure that the serialized code for the derived class is instantiated. And we need some identifier when we stick it into the registry. So here we've got some struct A. That shouldn't say task, that should say A. So there's a typo there in that slide. But so we've got some struct A, it's got a virtual destructor and a serialized method. We've got some B, and it's got a serialized method. Note the serialized method's not virtual. Why isn't it virtual? Well, it's a template. We can't make a template virtual. And it has to be a template because it's got to support all the different archive types. So that's sort of where the registration comes in. We've got the interface here uses templates to support all these different archive types. So can't make it a virtual, so you got to do this explicit registration. So here's what it would look like. You've got, first in the derived class, you got this base object thing. That's got to be there. That's going to tell us where it came from. Because we want in the record to actually have the information, what the base object is. And then here we've got this macro, and this macro just takes care of the registration for us. All right, so we'll talk a little bit about some of the alternatives here. So protobuf, I think, is the main one. Who here has used protobuf or has heard of protobuf? Who here has used Boost.Serialization? Uh-oh, hostile audience. I guess I shouldn't say anything bad about protobuf. Protobuf's actually a really, really good library for a lot of things. But I don't think for object transmission, it's the best solution out there. I think if you've got some network protocol, it's a really good solution. So it allows you to find kind of your custom protocol. You have these .proto files. It's got no non-intrusive support, to my understanding. And it doesn't interoperate with STL or Boost data structures. So the other one, who here's heard of S11N? Anybody? OK. So this is another sort of similar to Boost.Serialization. It supports multiple formats. It does have non-intrusive support. It does have built-in support for STL. But neither of these support sort of the feature I'm looking for, which is the derived class serialization through base class pointers. Now, why do I care so much about this? Well, it's because I want to be able to serialize std function, basically. So I've got some type erased sort of polymorphic wrappers that I want to be able to send over the wire. In particular, I want to be able to send over a representation of a function. And that's what we do. So let's talk about object transmission. So object transmission is just serializing an object and sending it over the network to another endpoint. Yeah. Let's go up to the microphones for questions. I saw like 3 hands go up. All right, microphone.
The previous one, the Boost.Serialization, where you were doing that, how backward compatible is that? Like, if you're serializing from one class, which has you added some data members there, and the other class, other program which is deserializing it, you don't have the data member. Will it crash, or will it still ignore that? You're adding something, you're not removing something. Will it just take whatever is there and put it here, and the one that is extra, it will just ignore it?
So I think it's not going to let you do that. It doesn't have any way to work like that. It's going to check the version, and it's going to give you a versioning error. So and if it doesn't give you a versioning error, then if you're not using versioning and you change the data structure and you try to read in an old data structure, then it'll just crash. Okay. Yeah.
Because protobuf is that way backward compatible, right? Kind of.
Yes. All right.
Could you clarify what you mean by derived classes? Because in protobuf, everything is derived from message, so it serializes everything by a message star. So in a sense, everything is derived class.
What I mean by that is that I've got some base class A, and I've got a bunch of different classes derived from it, and I want to pass to serialization a pointer to A, and I want it to correctly serialize that object. So maybe the object's a B, maybe it's a C, At the time that I don't write the code, I don't know. So it's...
Well, in protobuf, you don't define your own hierarchy. It makes up hierarchy for you, but whatever hierarchy it makes up certainly has derivations.
I think y'all are discussing two different things. You're talking about a message in protobuf, everything inherits off of protobuf.
Yeah.
He's talking about his classes that he wants to actually then pack up and ship across.
Well, in protobuf, you don't pack up your own class. You write a protobuf.
Right.
Protobuf gives you a class, which is derived from something or other.
So I see Robert Remy, who's the author of Boost.Serialization, raising his hand. So I'm going to let him handle this one.
I think I can contribute a little bit to this discussion. And this question comes up, what's the difference between protobuf and Boost.Serialization? It comes up frequently, and if you look on Stack Overflow, you'll see a couple of threads related to it. And although they're both related to passing data from one place to another, or from one time to another, they go about it in fundamentally different ways of looking at it. Protobuf, you specify your protocol, the kinds of data which is going to be in there that you're going to be passing, and then you write code to match your structure to that protocol. Now, this has actually a certain appeal because it means that since you've defined the protocol in more or less isolation or separately from your program, then you can make it portable to Java or some other thing, because it's your protocol is the fundamental driving force which the other programs that use this protocol are dependent upon. So that's one thing. Now, Boost.Serialization is totally, and it grabs the dog by the nose instead of by the tail. It starts out with your C++ data structures, and it generates all the protocol necessary to be able to reconstruct that at a different time or place, but it's very C++ specific. It uses all the C++ features to do that. So if you use Boost.Serialization, you have to write almost nothing, but it requires C++ on both ends to work. If you use protocol buffers, you define your protocol, and then you put code in your program to match the protocol. And of course, that gives the ability in another language or another circumstance to match that code to the protocol. The protocol is the central thing which everything else is dependent upon. In Boost.Serialization, your data structures are the central thing about which the protocol is dependent upon. Is that helpful? Yeah, okay. It's easier than it sounds from the way I explain it. But it's the question of where you start. In Boost.Serialization, you start with your data, and the protocol follows from that automatically. In protobuffers, you start with the protocol, and then you adjust your code to match the protocol.
It generates the classes for you.
It generates the protocol classes for you, but it doesn't generate your user classes for you.
Well, it generates the message.
Well, that's the point. You have a separate thing for a message, which your program then uses. In Boost.Serialization, there's no concept of that. It's only your classes, and the message is generated. It's an internal format, which is done totally for you. So it's if you want to have something that is portable to other languages or whatever, definitely you should not be using Boost.Serialization. If you want to do the job with the absolute minimum amount of effort on your part, and deal with things like, and have dealt with things like object tracking and all of that, then you should use Boost.Serialization. So they're really not competitors, they're more complementary.
All right,
So,
thank you. I think it looks like there may be some other questions. Let's move on, we'll do those a little bit later. We definitely have plenty of time for questions, but if it's questions on alternatives, let's sort of try to move that a little bit to the break. Thank you so much, Robert. I really appreciate it. It's good to have Robert here, because if I don't know anything, he certainly does. So he wrote the library. So the reason why I think that serialization is really good for object transmission is because when I'm trying to do object transmission, I've got a client that's in C++, a server that's in C++, and I don't have some defined protocol. I'm just trying to get the object from point A to point B. So object transmission, again, it's sending it from one machine to another machine. And so the way that I use it a lot in work is sort of doing remote procedure calls. So I want to invoke some method remotely, or I want to just do active messaging where I send some message. I send like an STD function over the wire, which is basically all I've been doing for the past 4 years of my life, is sending STD functions over the wire on supercomputers. So it's nice because it does simplify away your network communication. I don't have to worry about the underlying protocol. I don't have to worry about how to encode and decode or linearize my data structures. I just go and I just write those very nice and simple serialized methods. And they usually look a lot like what that coordinate one looked like, where I've just got some archive and name of the data member, and I just got a couple of those statements. Sometimes they're a little bit more complex, but it's usually very, very simple. Speaking of that coordinate, we're going to go back to that. So here's this coordinate. So let's say I want to send this over the wire. So here's the minimal sort of object transmission example. This is the client side. This is the server side code. We got a binary archive, so output archive. And so we're going to go ahead and connect to local. So no, this is the client side code. So this is the client side code. It's going to go and write to the server. So we want to send this coordinate to some server. So here, what happened to my laser pointer? There we go. So this Asio TCP IO stream is a special object that sort of just gets rid of a lot of that boilerplate for very simple examples. So this will sort of take, it works like an IO stream, but it'll write over the network. So I'm connecting to localhost 2000, create my archive, I got my coordinate, send it, done. So it's not a lot of lines of code. So this is what the server-side code looks like. So it's a little bit more. There's no Asio IO stream for the server side. So again, we've talked a little bit about this. Okay, we do have this one here for sort of doing the accept. We've got it going ahead and accepting from the client, and here's the loading. And again, very simple. And so this is our most basic example of sort of the object transmission. So if I was to do this with something else, it tends to be, it gets a lot larger. I got to deal with a lot more things. This is nice because it's very simple. I don't have to worry about the networking stuff. So now we're going to talk about active messaging. So this is sort of the main example of the talk, and it's very long. So if anybody has a laptop, I would encourage you to, if you're interested, you can go and pull up the code while I'm talking or during the break. I think the link for it should be coming up in a slide or two again. So an active message is a message that's capable of performing computations. So normally, like if you want that coordinate example, I was sending over data. So that coordinate was just data. But sometimes I want to send over like a function object, something that's not just data, but that has a capability to execute. So we're going to build a very simple runtime system. It's actually, if you understand, like we're going to go through this talk, and basically in a very simple example, I'll rebuild the thing I've been working on for 4 years. I mean, our version of it, our runtime systems, this big, massive 200,000 line of code thing, but you don't really need a lot of that code. It's basically just this 500-line example, just scaled out a little bit. So we're just going to use 2 threads per node, so we're not going to do anything that fancy here. So we're going to have an IO thread that's going to be running an IO service object event processing loop. So the IO thread is responsible for waiting at the OS system for stuff to happen. And then it's going to process it off. It's going to pass it off to a execution thread, a hot thread, which is going to be responsible for executing completion handlers. So both of these are going to have sort of very different performance characteristics. That IO thread is going to spend a lot of time not on the processor. It's going to spend a lot of time waiting at the OS level. The other guy is not. The other guy is going to mostly be doing stuff. So we're just going to use TCP, IP. And again, there's what the code is. All right, so the IO thread waits for the IO events. And it's going to invoke the completion handlers. And it's going to be responsible for sort of joining back to that execution thread. And the execution thread is going to do the maintenance computations. This is going to do the actual serialization and the deserialization. So sometimes that can have a little bit of work. I mean, you may have a lot of stuff, right, that you want to send over the wire. We'll talk a little bit later about the faster way of doing it. Instead of copying things into a buffer, sometimes, let's say you just got an STD vector. Well, if I have an STD vector and I want to send it over the wire, I sure hope I don't have to copy it into a buffer. Because it's an STD vector, I should be able to just zero copy it. It should be that I should be able to pass the pointer to that vector's data to the operating system, and it should be able to use that for the actual write. And that was the motivating example that got me to make this talk. Was 2 years ago I was thinking about, why doesn't our code do this? Why doesn't our code do zero copy? That's what all the solutions like MPI, all the sort of production solutions do, is they zero copy arrays. So the execution thread is also going to kind of execute our active messages. So the completion handlers are executed here, but they're really just going to,
I actually have a question on zero copy. I'm wondering if you have any measurements. So zero copy competes with the idea that whatever you send over the network should be compressed anyway, because it costs you more to send data over the network than to copy data in memory. So do you have any benchmark that show, like, is zero copy sending uncompressed data worth it? Because if you're compressing, you're copying.
I do. I have a whole, at the end of this talk, like the last 30 slides are purely tips and tricks. There may be some benchmarks in there. I will say this, most of what I do is on supercomputers, which is very different because I've got networks with low latencies, high bandwidths, and very frequently the trade-off is, the extra copy is pretty expensive, and just being able to send the data is fairly cheap. Really, the only thing I'm paying for most of the time is the expense of keeping the object around. And I have access to a lot of memory, so usually I don't really care about keeping it alive a little bit longer. So different use cases, it may be more of a thing. But really with zero copy, the only cost I think you're paying is that the object has to be kept alive, or that if you're working with that object again in your code and you modify it, then you have to copy it there. I kind of am under the assumption that if you're sending the object over the wire, that maybe you're sending it over there because somebody else is going to work with it and you don't need it anymore.
Right, if I was saturating 1 gig Ethernet already, compressing the object might help me to...
Yes, let's talk about that a little bit later. We can talk about compressing. We do some compressing of stuff, but I'm usually working with QDR InfiniBand, where it's very hard for me to saturate the network. I mean, very, very hard for me to saturate the network. I have to be doing an embarrassingly parallel problem to saturate the network and not have it just be a latency question. So, all right, so this execution thread, it's responsible for doing the maintenance computations. It's going to actually process sort of the user code. So the completion handlers are sort of done in here, but all the completion handlers are going to do is sort of talk to the execution thread and say, hey, this thing happened, do the actual responses. And it's going to be responsible for breaking the I/O thread out of the event processing loop when it's time to shut down. So it turns out shutting down runtime systems is not a fun process, especially when you've got a distributed system. So for many years, the way that our runtime system shut down was it just sort of crashed gracefully. And then there was a period of time when it didn't crash gracefully, it just crashed. You got your result, then your program segfaulted. We were happy with it because we got the result. All right, so let's talk about the data structures that we're going to use. So we're going to have this thing called an action. And it's going to be a base class for our active messages. An action just represents, basically, it's an STD function. It's something that abstracts away a certain, call signature. We're just going to use a very basic call signature. Then we're going to have this runtime class. It's going to be the thing that sort of abstracts away the services that we're going to provide. So those services are the sort of I/O, the execution thread, the connections. We're going to have an API for starting asynchronous writes, for opening connections, for scheduling sort of local tasks, and for starting and shutting down the runtime. And we're going to have this connection class, which is going to represent a connection to another endpoint. And it's going to hold a socket, and it's going to hold buffers for that particular endpoint. All right, so let's talk about the action. So this is what action looks like. So it's got a destructor, kind of boring. It's got a call operator, which is a pure virtual method. It's got a clone method, because I want to be able to copy it. And I've got a serialize method here. All right, so here's the reading interface. So this connection class, it's going to derive from enable shared by this. And enabled shared by this deserves a little bit of an explanation. So and I got this question in my other talk, which was sort of how do you manage the lifetime of connections? The way that you do it in Asio is that basically every connection that you create as a shared pointer. And then you just pass around shared pointers in sort of, as you're passing them around to the different completion handlers, it's reference counted, and you sort of pass the buck. So you kind of got this chain of completion handlers, and each guy sort of is passing it along. And if you're just talking to this one node the entire time, you'll sort of have this rolling wave of, hey, this guy goes away, but I've started another one. And so shared from this, what shared from this does is it allows you to get a shared pointer from within a class if that class was allocated with a shared pointer. Because basically what you want to be able to do is, hey, this class, I've got an instance of this connection. I know that the only way that I'm allocating them in this code is that I'm putting them in shared pointers. But I don't have the shared pointer. I just want to get to I want to get a copy of the shared pointer that references this thing. So it's some magic that allows you, within these methods here, to get access to the shared pointer. And that's why it's important, because inside of the async read, we need to pass the shared pointer to this guy, to this async read, so the completion handler there will keep this connection alive. Because it would sure be bad if it went out of scope during the middle of the read. So we got these sort of structures. So we got a reference to the runtime object. And we've got this socket. We've got the sort of the size of the input, the size of the current message. So that's sort of a buffered thing. We're not going to be queuing up messages. So that's sort of our buffer for the writing out of the message size. And then we're going to have an std vector of car that's going to be our actual buffer. As we're going to see, we're going to pass those along. So we've got a bunch of methods that aren't listed here that are kind of boring, but that are on the GitHub version, sort of the constructors, destructors. Then we've got these 3 asynchronous operations. So the other examples that we showed, we didn't talk about sort of this 2-part read, because we were kind of dealing with data structures where we knew the size, and it was kind of fixed. But if we've got a data structure like an std vector, we need to put some information about how large it is in. And when we're reading from it, we can't just do one reading operation, because we have no clue how large it is. So what we do here is we first kick off an asynchronous read, which is going to read just the size. And that's what this handle read size is, the completion event for when the read of this size thing is done. And then inside of there, we're going to kick off the actual read of the data. So the control flow kind of looks like this. You start off your read. The reads go to handle read size. Handle read size goes to handle read data, which then starts another async read. Sort of like that example of the echo server where we had that function f, which sort of looped back onto itself, because we always want to re-enter the processing loop. All right, so this is what async read looks like. So here's some error handling that I didn't remove. Of course, it's just an assert, so this is not particularly good error handling. But I'm in HPC, so error handling to me is just, if I get my data, it's all right if it crashes, as long as I get the data, right? I don't lose my job if the production code breaks. So the first thing we're going to do here is we're going to 0 this in size, this buffer here. And then we're going to allocate a new in buffer here. And notice that what's the assertion here? Well, we're checking to make sure that that in buffer is zeroed. Why are we doing that? Well, because, as I mentioned, we're kind of passing the buck of the connection. And the connection's sort of reference counted. We're not reference counting this in size and this in buffer, but we are passing it along here. So every time we do a read, we're sort of taking the buffer that's there, And we're going to sort of, that's our buffer. It belongs to us once we start the actual read of the data. So here we're starting off the Asio async read, so telling it what socket do we use. Here we're forming our buffer, and again, a buffer is just an address and a size. So in this case, the address is sort of this in size, and then just the size of in size. So that's the simple case. That's the same thing that we saw with the coordinate. And then we're sticking a boost bind in here, and we're using that shared from this, which is going to give us the shared pointer to the connection that we are currently in. And then we got this placeholder for errors. So anybody who attended my functional programming talk the other day will be comfortable with this boost bind syntax. But basically what this is doing is it's sort of creating from this method of handle read size, it's creating a new function here, which is going to have this here, and then it's going to have a placeholder for the error. Because the way that the calling convention for Asio async read, it doesn't know anything about the fact that this is a member function. It wants just a function that's going to take one argument, which is an error. So we have to convert from that calling convention to the calling convention of this handle read size, which is a member function. And so the way that boost bind works is that if you've got a member function, the first argument to boost bind can be a reference to an object of that type, or a pointer to that type, or a shared pointer to that type. And there's a bunch of other things, actually, that it can be. So I should really, yep.
Would std bind or lambda work there, or is there something special?
std bind would work. Let me think about if lambda would work. I don't, off the top of my head, think of any reason why lambda wouldn't work. You would have to pass in the shared pointer by value. If you passed in the shared pointer by reference, that would be bad. So you want to take the shared pointer by, you'd want to take everything by value. Except for in size, you would want to capture that by reference, because we're sort of taking ownership of that. Yeah, so you could do this with the lambda. The lambda would just have one argument. It would take the error placeholder. You could do this with std bind. This is the way it is because this example code was written a little bit a while ago, and also I didn't want to have example code that only worked with C++ 11. There's no reason to not make it backwards compatible. Any other questions on this one? OK. All right, so this is what the sort of the next part in our processing loop here looks like. So again, we've got some bad error handling, which is just if we've got an error, we're just going to break out of the loop. So this error code, as I mentioned before, that's a boost system error. So I don't really talk at all about what boost system error is, but basically just it's a way of representing an error. It's a little bit different from an exception. You can throw a boost system error. But it's useful here because in the context of Asio, we may have a lot of things that would normally be like an error num situation. So this is just sort of a nice abstraction. It lets us handle non-fatal errors without having to throw exceptions around. So you could come in here and then you could throw it. There's ways to tell Asio to throw instead of passing in error codes and stuff like that. So we're going to assert here to make sure we've got a buffer, because we should have allocated one in the last slide. Now we know what the size is, because we've just finished reading the size. What this completion handler has told us is, hey, your size is here. You can now, that buffer you just created, you can now resize it. You know how much data you need to read. So now that we know how much data we need to read, we can go ahead and start reading it. So here, this sort of shorthand for if you pass a vector into a buffer, well, a vector is an address and a size. It can figure that out. It's smart, so that'll create your buffer. And then we go ahead and we do the same thing with boost bind, where we're, again, passing the buck, we're passing the shared pointer. And now we're going to do the actual read of the data. And the read's pretty boring. So here we're going to have this buffer here. We're going to do this swap to swap in a null pointer to this sort of in buffer. And we're going to get back the thing that we allocated. And then we're going to go ahead and we're going to put the message, which has been read now, into the queue. So this is the handler, again, that gets called after the read is completed. So at this point, when we enter this function, we know if there's no error, then in buffer has been filled, and it's got the data. And from the last slide, we did the same sort of thing. We had the in size, which was 0. Well, in size is zeroed inside of the first function. And so then the last thing we do here is we go ahead and we start the async read again, because we want to be going in through this loop of, read, start a read, looking for something to do, read the in size, then do the next one, et cetera, et cetera. All right, I think, well, let's see how far can we get in 10 minutes. I don't know if I want to break right here. All right, I think we'll go to sort of the parcel queue. So remember, we had this sort of reading data flow. Now we've got this thing here that's taking in our messages. So the reason that we're calling this a parcel and not an action is because we haven't actually turned it into an action yet. We want to do as little work as possible in the read loop, because the read loop's happening in the I/O thread. And the I/O thread's job is to read stuff and not to deserialize stuff. That's something that belongs in the execution thread. Because again, there might be something else, some other message that's come in, so we want to immediately get to that next message. So that's the place where we sort of queue things. So here's what the runtime looks like. So we've got a map of connections, a map of shared pointers to connections for each different endpoint. Now, the last time I gave this talk, there was a discussion about having multiple connections here. But for now, we're just going to assume we just got one connection for each node, that we're not going to have sort of multiple connections, so we're doing multiple reads at the same time. So we've got this I/O service. Again, we've got our acceptor. And we've got that connections map. We've got some representation of the execution thread. As I mentioned in an earlier slide, the I/O thread's just going to run in our main thread, so we don't need a representation of it. We've just got those two threads, the main one and then the one we spawn off. Then we've got these two lock-free queues. So one that's this parcel queue, and then we've got this local queue, which is going to have the actual things we're going to execute. Then we've got this stop flag, which we'll use to shut it down. And there's some other members here that aren't important, and then there's some that are important. So we've got start. Yeah, that just starts sort of the whole event processing system. So that's going to launch the execution thread. It's going to start all the different event processing loops. We've got stop, which is going to shut things down very delicately. And then we've got run, which is going to do the actual exception of the connections. And that's the actual sort of event loop. And then this is the sort of main execution loop, and that the std thread that's the execution thread is going to run. We've got this serialized parcel and this deserialized parcel. So these are the two functions that sort of get applied to the things that are in that queue. So the deserialized one is going to be done once we've gotten the message and it's put into that queue, and then the serialized one is going to be done in the execution thread before we send it off to the write. And so we're going from, in the deserialized case, we go from that just vector of car into an action, and then we do the reverse there. All right, so the execution loop flow, it's just this loop. It's spinning. It's hot. It's not waiting or anything. And it's going to either deserialize something or it's going to execute something. And the reason that we don't see the serialize here, because the only time when we're going to sort of send a message is if something that the user's executing says send a message, and then that would be covered in the execution case. But the deserialized case is, we've received something, we need to react to it. The case of the send is something that the user has to initiate. So we got the two queues servicing here. So here's what the execution loop looks like. So we've got that stop flag, which we're checking to make sure that we don't need to shut down. And in the actual example, the reason that it's an atomic is because if we get an error in the I/O thread, we may want to signal here that we need to initiate the shutdown. Otherwise, the only guy who's going to start the shutdown is going to be in the execution loop. So we wouldn't need it otherwise. So the first thing we're going to do is we're going to look for pending actions to execute. This is a pretty basic scheduler design. So if you've got the choice in a scheduler between maintenance or doing actual user work that doesn't require maintenance, you want to do the user work first. You can do the maintenance later in a sort of aggressive scheduler. And then if we don't have any user work to do, then we'll go and do maintenance. So we have this std function, void or runtime, and we're going to go ahead and see if we can pop one from that lock-free queue. And if we can, then we're going to go ahead and have a scope pointer here, unpack this, and we're going to go ahead and execute it. We're going to call this std function. We'll talk about how we get that std function when we go to the deserialize. So the reason that we use std function here, we can stick the action into the std function. So that action class can be stuck into an std function. And if we can't find any work, we try to find a partial to deserialize and execute, because there's no real point in us going through and queuing that up there. So we go ahead and raw message pointer and parcel queue pop, yada yada, get the message, deserialize it, and act on it. Well, so then why do we have this one? Well, the reason is that maybe we have some work that we want to queue up locally that doesn't involve deserializing. So we're not actually, everything in this local queue, none of that is messages that have been deserialized. If we have the message that's remote, we just sort of immediately execute it. And if not, we're doing something local. All right, here's what the deserialized parcel looks like. So we've got this container device. This is from the Boost.Io streams library. This is sort of a way to turn a std vector into something that kind of looks like a stream. So we're building an IO stream that sort of goes into an std vector. And then we've got this action pointer, so our base class pointer. And we want to read from this binary archive into this pointer. So that's it. So we just go and do the read. Ta-da, we've gotten our pointer. It's been reconstructed from whatever it was. And I'm trying to find a good place to stop because we're about getting at time. So I think this is about it. So now we'll sort of piece this together. Now you kind of see this is where this comes in, feeds into the parcel queue. This is sort of what our little system looks like. And I think we're going to break here, and then we'll talk about the sort of write interface and sort of some little examples that use this little toy after the break. And I think if we've got a couple minutes, so if people want to come up and ask me questions that maybe aren't like group questions, feel free. I'll be around here during the break.